Hello and welcome once again for another EE324 video. Today we'll be discussing fluid systems. So generally what we're going to be dealing with, typically we will be assuming incompressible flows. So you can think of, in this case, the fluid will be a liquid. That's essentially what we're saying here. Generally, liquids produce incompressible flows, whereas gases, which are also considered fluids, may not have incompressible flow. In fact, it's compressible. So we're going to deal with when we're dealing with fluid systems, that's what we're going to focus on. Okay, and so we're just going to introduce in this video some of the variables, some of the equations, just like we normally do, and a few of the concepts, and then we'll move on from there in the next video with some examples. Okay, so let's look at the variables. This is not meant to be an omega, sorry. This is a W. This is W. It's also sometimes written as Q, and this is the flow rate. In fact, I would say probably most of the time it's written as Q, but your book, for whatever reason, chose W. And typically we measure the flow rate in cubic meters per second. The volume, which is going to be a capital V. This is going to be measured in cubic meters. The height, which is H, which is obviously going to be measured in meters. And the pressure, which is measured in newtons per meter squared. Okay, and we may work with absolute or gauge pressure. So absolute is the total pressure, including the atmosphere, basically, and gauge pressure is not. So let's look at a few of the concepts. And what you're going to find probably is that typically fluid systems, particularly incompressible fluid systems that we're going to be examining, have a nice relationship with electrical systems, right? So much like the rotational systems seemed a lot like linear mechanical systems, fluid systems seem to behave a lot like electrical systems. Okay, and so we're going to have this concept of hydraulic capacitance. So here we have C of H, which is given by the area divided by the density times the gravitational constant, the gravitational acceleration. Okay, the density and mass per unit volume. This is going to be the area. So the capacitance is going to be related to the area. This is going to be a change in the volume, the rate of change in the volume per the change in temperature, pressure, excuse me. So we will have dV dP basically for our C here. And then some of the other variables that we're going to be looking at a lot will be the time change, so V dot. Well, that's going to be equal to the flow rate in minus the flow rate out. And remember, we can also, this also might be written as Q in and Q out, right? So just as a reminder. So if I switch by accident between this, let's actually make that explicit. Okay, so we don't forget. The change in height per unit time. Again, these are all linear relationships assumed here. Is 1 over the area times W in minus W out. And the change in pressure per unit time is going to be 1 over that capacitance times W in minus W out. And so you should be able to obviously rewrite these in any way, like H dot obviously is going to be equal to W in minus W out. This is going to, and this one's going to imply of course that Cp dot is equal to Q in minus Q out, right? Okay. So these are a few of the relationships. We have this concept of resistance. We have two common types, which are turbulent and laminar. Okay, so we're going to have this concept of resistance. I'm actually going to start with the turbulent one. And how we know these relationships, by the way, is they can be measured in the lab. So this is where the relationships come from. So the basic idea is that W equal to K times the square root of delta P. Okay, so this is a which of course implies that delta P is equal to W squared over K squared. So the resistance here kind of looks like R squared, right? You can see this squared relationship here. This is in turbulent flow. Okay, and so then we can linearize this for laminar flow. So how do we linearize? Well, we can actually do the whole game of linearization, right? So we can choose, say, delta equal to w minus w tilde, and delta w, and delta p equal to capital delta p minus capital delta p tilde. And then we know, of course, that w should be approximately equal to w tilde plus dw d delta p evaluated at delta p tilde times lowercase delta p, which obviously means that w minus w tilde, which is our delta w, right, is equal to dw d delta p evaluated at delta p tilde times lowercase delta p. And then we can evaluate this term by taking that actual derivative. Dw d delta p evaluated at delta p tilde is going to be equal to k times delta p to the minus 1/2 divided by 2. And what we can then do, of course, is we can set now delta w equal to this. And we're going to note that delta p tilde is a single value. Not a variable. I shouldn't say a single value, is a value. Because there could be multiple equilibrium points, right? But it's not a variable. And so because of that, we can then just substitute in whatever that value is. So this just becomes all some kind of constant term. So if we let r equal to 2 times delta p tilde to the positive 1/2, because I'm dividing by this over k, then we get delta w is equal to 1 over r times delta p, or delta p is equal to delta w times r. So what we'll usually do is we say P is equal to W times R for laminar flow. Okay, and we should actually take a look at what laminar flow looks like, and we'll just let's call this RL, just so that we keep that in mind. We should have an idea of what laminar flow looks like. Laminar versus turbulent. Okay, so let's draw a nice little pipe here. Okay. And if we can get very nice straight line type flow going in here, we call this laminar. And typically, if the pipe is big enough, and the flow is slow enough, then the flow is laminar. Okay? For turbulent flow, however, it doesn't look like this. So let's have our nice pipe again. But this time I'm going to have some obstructions. Okay, so what the flow looks like here is, notice that when it comes up here, the only way it can go is by curving. This can still go straight through, but now the flow looks something like this. And when it comes out, because it's mixing and all of this stuff, we get something that looks like this in the flow. Okay, so this kind of chaotic mixing type behavior is turbulent flow. And we already saw what turbulent flow is, because this is how this has been measured. This is sort of the relationship for turbulent flow, right? Delta P is equal to W squared over K squared or something like that. So it's a squared-like relationship, unlike in this case where it's a nice linear relationship, okay? Then how about fluid inductance or inertance? This is due to inertia. Of the fluid. That one, at least I should say linear. That one is going to be delta P is equal to LF times W dot. Okay, so this should remind you of electrical inductance. Right? We had like an I dot term there. The last thing that we should keep in mind is this concept of conservation of mass. So I'm going to write down an equation here. Minus. So basically this is the total change in mass should equal the total mass in minus the total mass out. This should be pretty straightforward to understand. This can also be written, so this is going to be equivalent equation which is rho dot times V plus rho times V dot, where this is rho, of course, is, as we mentioned, the density, and V is the volume. Okay? So these are all the key kinds of concepts and equations that we'll be using, and we'll do some examples in the next video. Hope to see you again soon.